Hello, everyone, and welcome to Mobile Robotics Training Days. My name is Mike Oitzman. I'm the founder of the Mobile Robot Guide and an editor of robotics at WTWH Media, and I'll be your moderator today. This is the first day of our 2023 event, so welcome back this morning. And we're going to dive into a topic called the 10 key motion control technologies for mobile robotics. But before we get started, I have a few housekeeping items that I'd like to cover. All of the sessions during our Mobile Robotics Training Days will be available on demand, so you can rewatch them shortly after they end at roboweeks.com, which is where you registered for the webinar. All right. If you're rewatching a session, just use the same login information that you used today to watch this session. The slides for today can also be found in your screen's attendee resources window, and you can download a copy to your computer. You can personalize your experience by adjusting the webinar's window size and moving the widgets around on the ON24 control panel to make it look like you'd like it to. And at the end of the presentation, we're going to have a question and answer period, so please use the designated Q&A widget to submit your questions. Finally, if you have any technical difficulties, start by refreshing your browser first. This typically solves about 99% of the technical issues. And if you can always access our webinar producer by clicking on the help widget if you're still having problems. We've got you covered with all the latest news and information and education with our various sites, including the Robot Report, Mobile Robot Guide, Robotics Business Review, and Collaborative Robotics Trends. And I also want to invite any of you to attend our live Robo Business event, which is coming up on October 18th and 19th in Santa Clara. Now I'd like to thank our sponsors for today's event. Our silver sponsor is Performance Motion Devices, a world leader in motion control technology for life sciences, robotics, and industrial automation. PMD offers a wide range of advanced electronic motion control products, including integrated circuits, digital amplifiers, digital drives, and boards to our worldwide customer base, and you can learn more at pmdcorp.com. Electrocraft is also a sponsor. They're a global provider of dependable application-engineered fractional horsepower motor and motion products, and you can learn more about their offerings at electrocraft.com. All right, so let's get into today's session, which will be about motion control technologies for mobile robotics. Our speaker is Prabhakar. He's the VP of Engineering and Strategy at Performance Motion Devices. And in this webinar, you're going to take a deep dive into the standard motion control techniques, as well as some of the new techniques for achieving state-of-the-art control of motion and remote control devices. So welcome, Prab. The session is yours.
Thanks, Mike. Thanks for the intro. So just a quick overview on PMD. So PMD does, like Mike suggested, we do motion control chips and boards and drives that's used all across mobile robotics, lab automation, lots of different spaces. So today, what we would like to talk about is just 10 top techniques that we've seen used by a lot of our customers across the board, from mobile robotics to lab automation to medical device and surgical robotics. Just as you could see, we would kind of walk through each one and give you tips on a few techniques that you can use for these. So the first one would be the high torque to weight actuators. This is used in a lot of the pick and place robots. The second one is the precision force control, where an end effector is trying to grab onto an object. How do they accomplish that? The third topic that we'll try to cover is, if you look at a regular robot, an arm robot, it does a lot of non-Cartesian coordinate math. Like a SCARA robot that's on a gantry doesn't. So we'll kind of walk through how do you accomplish that. And then we'll move on to regenerative braking, how you can accomplish that with our chips. Then we'll move on to some more other topics on miniaturized components. We'll walk through modules, ICs, and motors, and how you can pick them. And the last few topics are more tied to optimizing efficiency, trying to do some compensation techniques for higher efficiency, and use of ruggedized encoders. So we'll kind of walk through one by one, and then we'll end with a few application examples, and then I'll just summarize what PMD does, and then we'll go to Q&A. So with that quick intro onto our first topic. So the first one was high torque to weight actuators. So the typical question we get when someone starts on a motion control project is, what type of motor should I use? So we created these charts that you could see on the right, which helps you kind of pick what type of motor you want to use. So it gives you the comparison between a brushless DC, a DC brush, in terms of the power to weight ratio, and what it takes to actually get to that power output. And in recent years, we're starting to see a resurgence of step motors, especially with the closed loop servo control, where they use a step motor as a two-phase brushless kind of setup, where they have an encoder, they get much precise positioning, but they get the higher torque output. As you can see on the curve on the bottom, when you run it in the closed loop mode, you can actually get higher torque to weight ratio on a stepper motor. So there are some applications, especially in mobile robotics, where some people are starting to use stepper motors for trying to add an encoder to it to try to get higher torque to weight ratios. So these are the keys, the power to weight and the torque output to weight, that get looked at a lot in terms of the robotics application. So this chart, we'll share this presentation with you guys. So this kind of helps you figure out where you are in the sweet spot and what type of motor to pick for your particular application. The other thing we tend to see is the use of linear servo actuators. So in this particular case, actually, as the illustration shows on the right, it's a rotary motor that the output is converted to linear motion. So as this illustration shows, it's a rotary motor that's driving, and then it's coupled together to drive a linear shaft. And in this use case, it could be a DC brush or a brushless DC motor. And there's a lot of other use cases that we have for actuators that we cover in detail in a white paper. So you can go to the PMD website to get it. But just to highlight this particular one, where you get pretty high torque, it's moderate accuracy and moderate speed. So we try to cover and compare all different actuator implementations. Obviously, in this particular presentation, we'll just look at one as an example. And then you can kind of look at that white paper to evaluate for your application, what type of actuator should you pick, or what type of actuator should you design for it. And in this particular case, you would require a strain gauge sensor or something for force control. The other common thing that we get a lot of, the other technique that's asked for a lot, and we get a lot of questions on, is in terms of precision force control. Obviously, you can use force sensors like a strain gauge to measure the force and act on it. But there are lots of applications where there's not enough space to put a sensor. So if you look at this particular example, right, it's a gripper or a screw cap applicator or one of those applications where the exact location of the object is not always known. So in this particular case, what you tend to do is kind of do it in two parts. The first part of the move is to just engage the object. And the second part of the move kind of establishes the squeeze force. And there's two techniques to kind of control the amount of force that's applied. So one of them, as this slide shows, is where the position kind of determines the force. So you program in the position. This is mainly used with direct drive motors. So you move the actuator towards the object, and then you stop the move when the desired force is reached. It's kind of equated to a position. And so during the arm move, the grip phase force may kind of vary. So the chart on the right kind of shows this particular use case where they kind of use the position and just program in the position, and they calibrate this ahead of time to figure out what force is applied. So you don't need a sensor in this particular use case. The other one is where you set an explicit force limit. So you can actually set an torque output threshold, and then you move the actuator towards the object. The trajectory continues moving, so even after the torque output saturates. So the grip force here is kind of maintained. So as you can see, once you reach the actual position, the grip force stops increasing, but then you can continue the move. The commanded position can keep increasing. So in this particular case, obviously in the previous one, we said the position kind of tells you what the force is. But in this case, the torque output threshold is set up to equate to the force. And so you don't need a sensor, but you can then continue moving across your trajectory and kind of fix the force at that particular torque limit. So these are the two common things that we've seen a lot of the robotics guys use, where they don't really want to use a force sensor, but this technique lets them kind of do that without having to use a sensor, but using a torque output or the position as a way to determine what force gets applied. So those were the first two. So the first was about actuators. The second one was about force control. The third one is actually a pretty common problem. So if you think about it, just to give you a background, right? So if you take a gantry, like a SCARA robot, it has a fixed XYZ motion. So you're commanding position and distance and everything on an XYZ kind of coordinate. Whereas in a non-Cartesian, if you take a regular robotic arm, like an ABB or KUKA, one of the automotive guys, it's all about non-Cartesian coordinates. So where the motion is kind of specified in non-Cartesian. So the system, the robot itself, has to do the math to kind of convert. So you have, if you look at it, you have a shoulder joint, an elbow, and a wrist, and you're kind of converting the spin and the angle into your commanded position. So there's a lot of math that has to happen to make that conversion happen. So this pretty commonly called inverse kinematics, and you're trying to figure out from an XY to your phi theta coordinates. And so there's lots of different techniques to kind of do this. Obviously, you can do the brute force, where you use a powerful CPU to do all the math for every move. The other one we've seen is a table-driven approach, where the math is kind of calculated and you have a whole set of points. You kind of look it up, and instead of having to do the math, you can load a table into the motion controller, and it calculates the inverse kinematics. So that's pretty common, actually, to try to simplify how complex a CPU you have to use in your controller. So especially if you take a mobile robot, in the traditional ARM robots, you can put a bigger CPU, but in the mobile robot, the inverse kinematic stuff, if needs to be done, can be table driven. So there's a bunch of techniques for it. We have a detailed white paper to show how it's implemented, and we can actually help you implement that. That's on the non-Cartesian math point of view. And the other problem that happens in a lot of these robotic arms is you have there's linkages, and that creates complex profiles. So what happens is the motor doesn't have a regular move. It rotates a little bit faster at some points and slower at other points. So to keep a load in a straight path, you have to do some sort of compensation. So the profile, the resultant move, is a little bit more complex. So it's not a trapezoid or an easy move. So what can be done is, with these inverse kinematic equations, you can compensate for them and kind of do this compensation in a table. So you take the previous regular math that has to be done, plus the complexity of the mechanics of your robot, and you could put both of those together through a table-driven approach without having to calculate this complex math. So that kind of gives you a quick overview on the non-Cartesian side. You can actually download a white paper which walks through all the equations, what can be done with a powerful CPU, and what can be done with a simplified table-driven approach. The fourth topic that comes up sometimes is on regenerative braking. So there's a white paper that we have that kind of walks you through what happens in regenerative braking. Right? So what you're trying to do is, when you're braking a motor, you're trying to, instead of wasting the energy through heat loss, you're trying to use the back EMF power to charge a battery. So this drawing on the right kind of shows the equations and what happens when you brake. And the next chart actually tells you the zones where regenerative braking happens. Right? When dynamic braking starts, you start getting into the regeneration space. So you use the back EMF, and as the previous picture showed, there's a couple of pins in our chips that provide this. So it indicates when braking is happening, and there's a shunt output. So you could add external logic or circuitry to charge a battery. So one is recognizing when you're braking, and two is getting this effective voltage and then dumping it onto an external circuitry that can charge a battery. So this is not that common in mobile robotics, but we're starting to see people asking the questions, or how do you actually implement it? So there's a white paper that we've written to show how you can implement them with our chips with external hardware. So we've covered 4 topics so far. Moving on to the miniaturized components. This is a typical question we get on a bigger robot where they have a lot of space. It's not a problem. But with the mobile robots getting smaller and smaller, there's a big push towards miniaturizing components. So this picture here kind of shows you, this is a controller on the left that was a typical size from 10 years back. And this is a newer controller that we've just launched. And it's only 1.5 inches by 1.5 inches. And it's pretty popular in the mobile robotic space, mainly because of the size, because they typically have to do 2, 1 per axle at the minimum, right? So one of them is controlling the front wheels and one of them is controlling the rear wheels. And so in a mobile robotics application, 1, they don't want the components to take up the weight, and 2 is the real estate that they have to actually implement these motion control products in there. So this gives you an idea of the difference in size and the weight. So if you look at the relative weight of the motion controller, it's only a percentage of the whole system. And obviously we've gone up in technology, it can drive up to 1 kilowatt of power. So this is a common request in terms of what's the smallest implementation that we can do. So this kind of highlights what you can do with a motion control drive. The second part of it, so this kind of highlights what we have within that. Within 1.5 inches by 1.5 inches space, you get a whole bunch of host interfaces. It can do up to 1 kilowatt, and it supports all sorts of host interfaces and supports this distributed architecture. So we could, where we've seen implementations where if you have, let's say, a 6-axis robot, the host is talking to the first controller over one CAN or Ethernet or serial. And then on the back end, we have an expansion network that lets you virtualize. It makes it look like a single 4-axis chip or drive, but it has multiple drives in the back end through an expansion network. So there's techniques that we've highlighted in a lot of our resources where it highlights the differences between a centralized architecture where all drivers are connected to the host. So it kind of shows the number of commands and the wiring that's required, and then a distributed architecture where you have the first controller tied to a bunch of them to virtualize it. And the other part of the miniaturized option is obviously ICs. So we have seen applications where you have a robot arm and you want to kind of position the motor somewhere in between, and you want to make a circular board. So you can't use a drive product, and you want to design a custom card. So that's where our chips, they get as small as 7 by 7 millimeter, and then you can design your own custom circular card or unique shape, so you can fit it right behind on the back end of a motor. And it provides all sorts of capabilities from profiling like S-curves and trapezoids to contouring and feed forward and all sorts of compensation. So this is a full-blown motion control chip where you could have distributed control where the chip itself can do most of what you have to do, and you're just sending high-level commands to the chip. So this is pretty common when the volumes are high and you have a very unique shape that you're trying to make the card to implement, and you have a small space. So like in robotic arms, they tend to typically go towards using our chips and doing their own custom board for their implementation. In some cases, we've seen where they've done a circular board with the holes so that the cables can go through the gap in the middle. So it's unique to the mechanical design. So the other part of it is obviously in terms of the ICs, as you could see, right? One option is you buy a drive, and so we've kind of analyzed what it takes to do a design. It's a build versus buy kind of decision, right? So you can actually just buy a drive, and if that works and the volumes work, then it's the best solution. But if you have a unique shape, then this white paper that we have kind of highlights, okay, what are the unique things that you have to take care of if you do your own design with our chips? So it kind of walks you through the number of months. So it's a couple of a couple of man year application, right? In terms of how long it takes to develop versus using the drive is quicker. So it's a trade-off. So we've kind of done some math and analysis, and we give you a white paper which kind of highlights the build versus buy decision, when to do your own board, and at what volumes does it make sense. The next part of it is in terms of the miniaturized components, the motor side of things. We had talked about closed loop steppers. So there's a lot of really small form factor motors that are showing up that are stepper motors. So they have smaller teeth, and the rotor structure of these small step motors, they are a challenge to machine at a reasonable cost. So what ends up happening is, to get smooth motion with these super small motors, the controller has to compensate. Like, there's a bunch of servo techniques that are available that kind of dampens the resonances that happen with these inaccuracies in machining. So as you go to a smaller and smaller stepper motor, it takes a little bit more effort to get smooth motion and to get position accuracy. So we have feed forward other techniques to kind of compensate for these inaccuracies in your motor. And so you're able to use these tiny motors in some of these applications and compensate for them on the controller side with unique algorithms. And obviously the other part of it is trying to figure out the effectiveness. So in some cases, they have the capability to add an encoder to a stepper motor. Some cases they don't. So this kind of highlights the differences between running a stepper open loop versus closed loop. So you tend to have a little bit more noise, and there's a little higher heat generation because it's not always at the optimum spot when you're moving with a stepper. The closed loop kind of gets you the benefit of being quieter. There's an added cost of adding an encoder, but then you get much higher position accuracy. So we walk through the trade-offs between both approaches and kind of saying, okay, when should you use a closed loop approach, and what is the cost for it, and what are the benefits for it? So we kind of highlight all these unique comparisons between open loop and closed loop. We are actually seeing a lot of implementations moving to a stepper motor because of the smaller size and higher torque, but they're starting to do it in a closed loop fashion. So the last few things that we wanted to talk about, one is optimizing efficiency. So this is just a laundry list. Is a white paper we've gone through in detail about trying to use these techniques to kind of get better efficiency from your application, right? So as the motors have gone smaller, the inductance they're pretty low inductance motor. So where the current control is not as efficient as when you have higher inductance motors. So there's techniques to increase the effective coil inductance by either in hardware or other techniques. We've walked through those. And as you start using low inductance motors, you want to try to get to higher PWM rates. So our products support up to 120 kilohertz PWM. And so if you run it at the higher PWM rate, you can kind of offset the low inductance effects. And obviously the other techniques include FOC that's built into our chips and drives, trying to use a lower bus voltage, right? So you have kind of lowers the current ripple that you see. And you kind of check your commutation to reduce efficiency. Misalignments in them kind of reduce the efficiency. So there's techniques to optimize that. And the last part of it is the holding torque that's required with stepper motors. So kind of fine tuning those. So really helps to have a motion control partner that can say, okay, this is, if you picked a motor, it's a low inductance motor, we can walk you through a whole bunch of techniques that you can use to, one, spin the motor at the highest RPM that you can, but two, doing it efficiently and with less noise. So we have a checklist and we can walk you through techniques that you can use to kind of make it work the same way that you're used to with higher inductance motors. The other problem we typically see is this smart feed forward requirement, where, as we talked about, where you say you have there's compliance in your linkages. So it's a linear axis, but then you have the motion, there's variances in the mechanics of it. So what we've done, you can actually create a torque to deflection table and do a dynamic compensation during robot motion. So what we end up doing is adding a feed forward table that gets added ahead of the motion and compensates for all these mechanical inconsistencies. So this is a particular example where there's an elastomer or a belt or something. And so you're trying to take out those non-linearities with a compensation table. We've also seen this used for other use cases where they have actually an older encoder that's not as accurate, and they can't afford to use a higher cost absolute encoder. And so they kind of use this feed forward so they can calibrate it in the lab, use and compensate the position feedback. So they add a feed forward table. So the position feedback that comes back gets compensated to a much more accurate, as if it looks like an absolute encoder. And then it's used in your position loop. So there's techniques to use to kind of get a lower cost hardware implementation to perform like a higher cost absolute encoder with feed forward tables. So we can work with you as a partner to say, okay, once you pick these components, we can try to help you cost optimize them and provide you motion techniques to make them work better. And so this was the one where you use the torque to deflection table. So you kind of calibrate it, you calculate it, and then you apply the profile generator applies the torque to deflection table. It's applied as a beginning entity in your PID loop, and it compensates for those errors. And so this chart kind of shows you the details of it. And we have a white paper that kind of walks you through the details of, one, how to, this torque to deflection table is something you do in your lab before you ship the machine. You calibrate it, and then you populate the table in our chips or drives, and then you can get much better positional accuracy with it. So the last topic we've seen a lot of is these ruggedized encoders. They are hermetically sealed. So where you have these magnetic encoders that are sealed, that are starting to see more use of. We are also starting to see sine cosine encoders where, like, if you have a microscope stage and you're getting to nanometer precision, you need these sine cosine analog encoders to get the much higher positional accuracy. So they're kind of used in combination with the quadrature encoder, and we're starting to see more of it used. And we have absolute encoders. You're starting to see more of them with BIS newer interfaces, like serial. It used to be SSI, and now there's BIS and newer serial topologies where you can daisy chain multiple encoders. And we've also seen people using multiple encoders for safety. So they would have an encoder for position, loop, and feedback, but they would have a second encoder for safety. So if it goes out of bounds, and they use the second encoder as a check to shut off the axes. So we've seen unique use cases where there's multiple encoders used per axis, and we've also seen cases where they daisy chain them. So there's unique use cases for ruggedized encoders and serialized encoders. So we can walk you through your particular application and kind of help you design what it'll look like. So that's just a very quick snapshot of the top 10 control techniques that we've seen. Obviously, there's a lot that goes behind each of those, and you can always reach out to PMD and we can help you design your system, but also give you white papers and resources that you can use to kind of work on any one of these techniques for your particular machine design. So I would like to kind of switch to application examples to highlight some of these. So this is a robotic arm implementation, right? So this is kind of showing this, what I was talking about. This shows an N series drive, our newer drive. This shows a rendering of how big it is. It's very small. It's an inch and a half, so it can fit right in the axes and next to the motor. So you minimize the wiring. So all that goes from axis to axis is just power and the communication. So CAN or Ethernet. So it minimizes all your encoder feedback. So it reduces the weight of the wiring and makes it more reliable. So you have the drive sitting right at the motor. And obviously, if you have a super unique design, you can use our chips to do circular cards and other things where you have cables going through. So this kind of highlights a bunch of the techniques we saw. So the drive itself can implement most of the techniques that you saw highlighted before. So this just gives you a visual rendering of a robotic arm with our N-series drive. The other one we talked about, which is very common in lab automation and a lot of automation spaces, is the gantry application, where it's mounted as a single card. It's a 3-axis card with N-series drives in them. So they're controlling X, Y, and Z, and you're running the wiring across. So this is a second example of how these drives get used. And the last application example we want to highlight is, it's actually in surgical robotics, where they wanted to have a handheld stand that's battery operated, that's low power. And here it shows two of our N-series drives in a battery operated mode. And it has controls for their surgical robotic steps. So this just gives you a visual of how you would implement your system and how the cards would look in your final design. So with that, I'll kind of switch over to just quickly giving you highlights of PMD, because I wanted to try to give you time to ask your questions. So PMD has been around for 20 years. So we control more than 6-7 million motors worldwide. We typically use for super precise motion control. Like if you think of microscope stages, it's used a lot in mobile robotics. So we kind of provide the user a progression, right? So depending on the volume, the digital drive is very quick to start, or buying a card, and if the volumes go up, they can do their own chip design. So we actually had a mobile robotics vendor who started with our card, a 4-axis card, was able to do a proof of concept, show it to the VC, show it to their customers. In parallel, they're designing their own card with our chips. And all of them use C Motion. It's a C-based SDK. So you can write your software for the board and then transition to your own chip-based design. So it kind of gives them a quick start for prototyping. They can use our board, just get the software going, and later on switch to their own cards. So that's a pretty common progression that we've seen with a lot of our customers. And obviously, like you saw with the 10 motion control techniques, what we're trying to highlight is there's a lot to motion control. Obviously, it looks simple. You can download off-the-shelf open source software, but it's all in the expertise, right? It's about tuning. How do you get the positional accuracy? How do you get your final machine working? And how do you overcome mechanical deficiencies in your design? So you tend to want to have a motion control partner that you can just bounce off ideas. We do schematic reviews and layout reviews and kind of walk you through the software architecture. Obviously, we work with thousands of OEMs, so we've seen lots of different use cases where things have gone really well, and we've seen a few use cases where things have not gone well. So it helps to have that partner work with you. And obviously, our ICs and drives have all the motion control techniques built in, right? S-curve, FOC, current control, all in a package. So it kind of helps you focus on what your core expertise is and not have to worry about all the basic motion control algorithms. So with that, the last is just a quick quote from one of our partners. It's an automation partner. What they did is they started off with a PMD chip-based design for one of their vendors, and they've standardized on it. They get to market way faster with all their vendors, and they keep reusing that design. We see that with a lot of our big lab automation OEMs. A lot of them have designed their own one-axis card with our chip and tend to reuse them across designs. So with that, I guess we'll switch to Q&A. I'll send it back to Mike.
Great. Well, thank you, Rob, for that great discussion. Pretty detailed there. And we still have time for questions from the audience. We'll be getting a few here during the session. So if you haven't already, please use the Q&A widget in your console to submit your questions. And so while I'm giving you a chance to do that, we've got a few here that we can start with in the first question related to the idea of distributed versus centralized motor control. What are some of the benefits maybe of distributed versus centralized motor control for a robot?
Yeah, so what we've seen is if you take the big robotic arms, most of them are centralized. So they have an external CPU, right, a controller. They do field bus or EtherCAT to the drives, and the central controller is doing all the profiles and the motion planning and all that, and they send PVT points to the individual nodes. So which works well when you have a lot of space for a bigger CPU. So if you look at a mobile robotics application, so we have two examples. One is with our drives right at each of the wheels. So they have independent four-wheel motion. Mm-hmm. And in that particular use case, they don't have a central controller, and they take one of our drives. We can download code to it, and they make it the master, and they daisy chain the other three. So it's a distributed architecture. So the sensor data is coming back, and the first one talks to a Wi-Fi controller that can upload data to the cloud. The other implementation we've seen is a one per axle. So you have two drives, and there's one per axle, and there they have a CPU on board that's collecting all the sensor data. The drives are just doing the position loop and the current loop and all that. And so the central controllers, there they have a centralized architecture where they put both the drives in a flat network. So that's the comparison. So you can have a flat where you have all the drives in each on the main controller. The thing is you have to send update commands to each one, right? So the communication that goes between them increases. The distributed architecture is the host is talking to one, and then there's a second network that's used in the back end to talk to the slave drives. So it depends on your machine design, and we've seen both used. And it also depends on if you have sophisticated sensors and vision and stuff, they already have a central CPU, then they try to go with the centralized approach. But if they don't need a big CPU as a centralized processor, then a distributed architecture with our drives being the host works too. So, and there's cases where, like lab automation example, right? They want to talk to one entity that acts like a 4-axis device. So they prefer a distributed where they're only talking to one node, and they're sending commands saying, oh, do this on X, Y, Z and 4th axis. So they don't want to talk to each one and say, okay, X axis do this, Y axis and so on. So then a distributed architecture where they're sending commands to one, getting status back from one, and then the first one is taking it and putting it on the expansion network to the remote. So there's pluses and minuses to both, and it depends on the machine design.
Interesting. So there was another question, I think you sort of answered this, which was synchronizing motion across multiple axes. That would, certainly in the case of either distributed or centralized motion control, you're still synchronizing set points, trying to get all the axes to work in coordination with each other. In the case of a mobile robot, the motors for the wheels starting and stopping at the same time. Is that correct?
Yeah, so we have in our chips and drives, we have a sync signal that you can tie between the drives together. What that does, it it synchronizes the PWM loop. So within the chips, there's a PWM loop that's running, and all of them start the whole PWM interrupt cycle at the exact same point. So if you command a position on each of these chips, they are at the exact time. So that's how they synchronize across. So we have pretty elaborate synchronization between the chips and drives. And the other advantage is you can actually mix and match drives and chips. So we have had one customer that has put an N series drive on there as a master, and they put chip-based stuff for remote axes that are smaller axes, lower power output kind of stuff. So you can synchronize across our products, and you can connect. There's a sync signal that kind of synchronizes between the chips.
So theoretically, then you could put a motor on a conveyor topper on top of a mobile robot that would also be controlled and synchronized
Correct.
potentially,
Yeah.
and or mobile manipulator or mobile axes that are doing some actuation with something on top of a mobile robot.
Correct. Yeah, we've seen in one particular use case where, to your point, they have like a gantry and a robot arm on top of a gantry. So the arm is moving linearly on an x-axis, and they have a 6-axis, a 4-axis arm on top of it. So they want to synchronize the position of the arm plus where it is in that axis. So we've seen that use case too.
Interesting.
Obviously, mobile robots are getting more sophisticated, right? They used to be vision-based QR code scanning things, and now they're fully autonomous, right? Self-navigating equipment. So we haven't seen a lot of regenerative braking requests for mobile robots, but we suspect over time, as they start carrying bigger payloads, instead of wasting energy, they can recharge their batteries.
Yeah, it's interesting. Now, I have another question that came in, again, still on the same topic, but maybe this question is specifically about using EtherCAT to communicate between your drives and your control boards. Maybe just recap all of the various ways that you can synchronize the different drives. What are the ways?
Yeah, so right now we support regular Ethernet CAN serial. So we are working on an EtherCAT drive product. So we've had customers who use EtherCAT who use our chips. So our ICs sit on the back end of a EtherCAT slave controller. So they've done their own board that is EtherCAT that uses our chips for the current loop, velocity loop, position loop. And they have an EtherCAT slave controller chip. So we've seen, obviously, we are in a bunch of designs with EtherCAT that the end customer has put the EtherCAT slave controller. So on our first gen N series drive, it doesn't natively support EtherCAT. So we are working on a newer product that will natively support EtherCAT on the drives.
Interesting.
So in that particular case, with EtherCAT, obviously it has the distributed clock, right? It has the DC synchronization. So the EtherCAT packet itself has the synchronization. It's not a separate signal. So in our chips, if you do your own board design, there's a separate signal, sync signal that goes between the chips to synchronize them. In the EtherCAT application, it'll be on the packet that comes across. You still need one of the nodes to be the timing master. It has to have a really good clock that everyone can time off. So our next gen product would have native EtherCAT on the drive. But
All right.
they really have to implement EtherCAT right now. They could use our chips and put the slave controller. So that's what a lot of our bigger customers have done, because they want, it's a much higher volume, so they don't want to use a drive product. They want to use our chips, and then they put the slave controller where EtherCAT is needed.
And do you support the path planning? You talked about inverse kinematics and trying to support path planning across multiple axes, assuming you've got a kinematic model for that, as well as other custom motion features?
Yeah, so what we tend to do is on the chips and the drives, we call it UDPM, it's user-defined profile mode, where what you end up happening is, say a mobile robot, right, has to go from station A to station B. It could be a whole bunch of moves, right? It has to traverse a bunch of moves. So instead of the master commanding it for every segment, you can load a table. So you can actually load a table with a whole bunch of points that the robot has to traverse. So at the end of that whole path, it'll give an acknowledge saying that path is completed. So there's off-the-shelf planning software that can compute. So if you look at the mobile robot in the warehouse, so they have off-the-shelf mapping and planning software that would actually compute points. And what we provide the capabilities on the drive or the chip, loading a table with 10, 20, 30 points. So we'll do the whole sequence of points, and we'll give you a status of where you are in that path. And so that's very common because the update rate that you provide, if you have to provide an updated position every segment, there's a lot of communication that's happening from the central controller to the slave.
Mm-hmm.
This UDPM table thing, it doesn't have to send it as often, right? It can send a whole path and then get status back and do the next path. While in parallel, it's planning the next set of moves in the central controller, in the path planning of open source software, and then you load this table. So it's very popular. It's used a lot, where they kind of segment them into sections and they load a whole table for a whole set of moves.
Interesting.
So it's trying to take more sophistication, right? That's usually in the central bigger CPU, and trying to put it in a drive. So you're giving them more capability in the drive. So it's already doing profiling and all sorts of capabilities, right? So you're just sending high-level commands, and now you can load a whole path ahead of time.
Interesting. And what's the maximum number of axes then that you can be controlled by one of your standalone drives?
So the drive is a single axis. So you need a drive per axis. So on the chip side, we have two flavors. One is a single axis chip, and the other is a 4-axis. It's a 2-chip solution. So it can do 4 axes at a time. The drive itself is 1 axis. But the drive is pretty small. So if you look at our module, it's only 37 by 37 millimeter. So you can put that per axis.
Got it. All right. Well, Prab, that's about all the time we have for this session. And again, if you're listening to this on replay, you can still ask a question after the fact. Those questions will be emailed on the Prab, and we can close the loop on, so to speak, pardon the pun, on your questions at any time in the future. So thanks again for this session on the topic of 10 key motion control technologies for mobile robotics. And I just want to remind everybody that our Mobile Robotics Training Days continues on Wednesday, September 27th, 2023, with a session about everything your parents never taught you about AMRs. And once again, thanks to Prab Gowrisankaran for sharing his knowledge with us today. I also want to thank Performance Motion Devices for sponsoring this session. You can learn more at pmdcorp.com. Also, thanks to Electrocraft for co-sponsoring this session. You can learn more about Electrocraft products at electrocraft.com. I also want to thank our producer, Lindsay Harvey, and the rest of the WTWH webinar team for all their hard work behind the scenes on this series. My name is Mike Oitzman. Thanks again, everyone, for attending.
Thank you.